We'll go immediately into the business meeting, which will be about half an hour starting at 5 o'clock in this room.
Hi, everyone. So I'm Shruti. I'm going to be chairing the last session of the day on secret sharing and ORAM. The first talk is going to be by Devesh Agarwal on secret sharing, randomness, and random list reductions.
Thanks, Shruti. So this is joint work with Eldon Chung, Maciej Opremski, and Joao Ribeiro. So uniform randomness is prevalent in many applications in computer science, including randomized algorithms, many crypto constructions, distributed protocols. So it's present in a lot of places, but can we really generate uniform randomness? So in an ideal world, we would assume that there is an oracle. So our computer behaves like an oracle that produces a random bit, which is 0 or 1 with probability half. So if you call this oracle n times, you will get a bit string, which takes any fixed value with probability 1 over 2 to the n. But in reality, this is too good to be true. In reality, when we generate randomness, we typically, the minimum assumption that we can make is that it is hard to guess this random variable x. So equivalently, the probability that x takes a certain value x is upper bounded by 1 over 2 to the k, which is equivalent to saying that it has min entropy at least k. So k is some number less than n. So we asked this question whether we can use such a source for crypto applications. So the way to use the simple idea to use this is if we can extract uniform randomness from the source. Let's say there's an algorithm that takes this source x as input and outputs a uniformly random source. Unfortunately, we know that deterministic extractor is impossible for these min entropy sources. So there's no extractor that takes any arbitrary min entropy source and outputs a uniformly random source. So we asked this question whether we can still build crypto primitives from such min entropy sources. And actually, this was answered in the negative by Dodis, Ong, Prabhakaran, and Sahai in 2004. So they showed that a bunch of these crypto primitives cannot be built from min entropy sources. So in particular, they showed the impossibility from block sources. So to summarize, so we have uniform source or very close to uniform source and a source from which you can deterministically extract. So from these sources, we can easily build crypto primitives because we can just extract randomness and then use it to build these crypto primitives. But from block sources or min entropy sources in general, we are not able to build many crypto primitives. So the question that we want to ask is, what are the crypto primitives? What crypto primitives can be built from some weak source that is not extractable? So is there some source in the middle here, which is still good for crypto and which is, not extractable? That's the question that we want to try to understand. Whether there are any sources from which we cannot extract, but still they are good enough for crypto. So in a kind of breakthrough result, this was answered for encryption scheme by Bosley and Dodis in 2007. What they showed is that if you start with any encryption scheme, you look at the source that you need for this encryption scheme, then you can extract from this source. And the idea was simple enough that I can describe in a single slide. So you take, let's say the key is a random variable. This is a key sampled from the source used for this encryption scheme. So what they do is they extract from the uniform randomness from the encryption of a fixed message 0 under this key. So the first observation towards the proof is that the encryption of 0 looks statistically close to encryption of uniform message. So this is using the security of the encryption scheme. And the encryption of a uniform message can be written as a convex combination of encryption of a uniform message for any fixed key k. So where k is any fixed key in the key space. So you can write encryption of k and uniform message as a convex combination of these. And then observe that because we can decrypt correctly, so this encryption of a fixed key and a uniform message is actually a flat distribution over 2 to the m ciphertext. So this 2 to the m came out as 2m when I converted to PDF. But it's so it's 2 to the m ciphertext, And this is a flat distribution, which means that it is uniform over some set of size 2 to the m. And then it is well known, and it's not too hard to see that extraction is possible if you have a not too large number of flat distributions. So if you just go over, the number of flat distribution that we are looking at is just the size of the key space. So we can extract from that. So that was basically at least one of the main results in this paper. We look at a related question, which is 2 out of 2 secret sharing. So here, a message M, we want to share it between 2 parties, such that the first party gets the share L, the second party gets the share R. And the property that we want is that one of L or R does not reveal any information about M, but together they can reconstruct the message. I give a simple observation here that encryption is actually also a 2 out of 2 secret sharing scheme. You can basically take the first share to be just the key K, and the second share to be encryption of the message with this key K. And it is not too hard to see actually that if you look at just one of them, let's say you are given just the key K or just the encryption of the message, you will not be able to recover the message from that. But if you're given both, then you can just decrypt. So this is a special case of 2 out of 2 secret sharing. So the question that we want to ask is whether 2 out of 2 secret sharing in general would imply extraction. And this was actually a question that was asked as the main open question in this paper by Bosley and Dodis. And I started looking at this question in 2012. And I thought, like, back then, how hard can this question be? It's a small generalization of this encryption scheme, so it should be quite easy. But after 10 years, I think it's quite a hard question. I'm not going to be solving it today. I'm going to show something weaker than this. So let me try to explain the difficulty, although I'll not do justice to the 10 years. So suppose we use the same idea as encryption. We try to extract from one of the shares, let's say the left share, right? So we take a fixed message 0, and you look at the left share K is 0. Then what you can do is something very similar. You can say that this is statistically indistinguishable from left share of K with a uniform message because essentially, as we just said, that from one of the shares, you should not reveal anything about the message. So that still works. And we can also write this as a convex combination of left share with fixed key K and a uniform message, where K goes over all the key space. But unfortunately, from a single share, this might not have any entropy. So we might not be able to, get anything out of this. Although you can write it as a convex combination of these, from single one of them, this might not give you anything. So, if you want to kind of think of this example, that I just mentioned, that encryption scheme is a 2 out of 2 secret sharing scheme. If you look at one of the shares, let's say just the key K, that would not, you would not have any entropy if you fix the key K. So we consider this question for leakage resilient secret sharing. So what I mean when I say leakage resilient secret sharing, so you are given the same secret sharing scheme, like with 2 shares, left share and the right share, and you are allowed to leak 1 bit from the left share and 1 bit from the right share, and then you want the same security guarantee still. So what we show is that leakage resilient secret sharing actually implies extraction. And here's a rough sketch of the proof. By the XOR lemma, we can assume that F and G actually leak not 1 bit, but T bits. The error blows up by a factor 2 to the T. And then we're going to extract uniform randomness from F of K and a fixed message 0 and G of K and a fixed message 0. And notice that since we said that we should not lose much by basically giving this information, so this looks statistically close to F of K and a uniform message and G of K and a uniform message. And again, we write this as a convex combination of F of KU, G of KU, where K is now any fixed key in the key space, just like earlier. So now the crucial observation is that this F and G can be arbitrary. We said that this works for any arbitrary leakage function. So we can choose F and G in such a way that F of KU and G of KU have high min entropy. And this is kind of the main non-trivial step in this proof that I don't mention here. So final observation is that extraction is possible, not just from from a small number of flat sources, but also from a small number of min entropy distribution. So we use that to conclude the proof of this. One primitive that has been very well studied in the recent years is non-malleable codes in the split state model. So actually that is also a non-malleable code in a split state model is also a leakage resilient 2 out of 2 secret sharing scheme, and which means that you cannot have non-malleable codes in the split state model without extractable sources. So you need extractable sources to be able to build these non-malleable codes. And maybe it's kind of interesting to contrast this with the AMD codes, which can be constructed from an entropy source. So these are these tamper detection codes for a certain kind of tampering. So you can actually construct those from an entropy source. Okay, so just to vent out our frustration, we introduced this new notion, randomness reductions, which basically, so since we were not able to resolve the main open question, we said, okay, let's study what all we cannot resolve. So so this is randomness reduction is basically you want to reduce a primitive A to a primitive B without additional randomness. So basically you are given a construction of A, you want to give construction for B without introducing any more randomness. So this would immediately imply that if you have a construction for A that does not require extractable randomness, then you have a construction immediately for B that does not require extractable randomness. So example of such a reduction we already saw, the encryption reduces to 2 out of 2 secret sharing. So we studied for what n, t, n prime and t prime can basically NT secret sharing. So T out of n secret sharing can be converted to T prime out of n prime secret sharing without any additional randomness. So we show many different reductions for different choices of n, t, n prime and t prime. So here's a simple example. Let's say n prime and t prime is 2. Then we can get a simple reduction by just giving any t minus 1 shares to one party and any one other share to the second party. And that is a valid 2 out of 2 secret sharing scheme without any additional randomness. So it motivates what are called distribution designs. They have been studied in the literature actually. So where you want to distribute n shares into n prime sets such that any t sets contain t prime shares and less than t sets contain less than t prime shares. So it's a nice combinatorial structure. And we find distribution designs for several different choices of n, t, n prime and t prime. In some cases, these designs are actually tight and cannot be improved. So we have several different constructions in the paper, different such reductions in the paper. So this basically implies that if 2 out of 2 secret sharing implies extraction, then I mean, because of the reduction that I just mentioned, then T out of n threshold secret sharing implies extraction for any T and n. So extracting from 2 out of 2 secret sharing might be harder. And so maybe most of our effort went into that. So maybe hopefully it motivates our main open question, whether we can extract randomness from a T out of n secret sharing scheme. Maybe that is slightly easier than extracting from a 2 out of 2 secret sharing scheme. So it's a very fundamental question, which hopefully this work would motivate kind of trying to understand this better.
Thank you. Questions?
Yeah.
Is there any hope in non-random randomized reductions, but like they use bad randomness? Because you focused on randomless reduction.
I mean, I know so little about this problem. I mean, what can be done that I have a hard time kind of saying that something can be said there. But I mean, so the simplest we thought of basically without using any additional randomness, because then you immediately get an implication. We didn't even go the route of trying with some small randomness because we understand so little about kind of what is going on about how to extract that we did not want to complicate it further.
One source that's really hard even to define. Part of it is going to be used for the primitive part of that.
Uh, Okay, given the time, we could take more questions offline with Devesh. Thank you. Let's thank the speaker once again. So the next talk is on leakage resilient linear secret sharing against arbitrary bounded size leakage family. The talk would be given by Hai Nguyen.
Don't press this last one. Okay, so this now. Okay. Okay, so thank you for the introductions. This is I work with Maji, Anat, Tom, Linguan, Shiu, and Albert. So let me start with the notion of secret sharing, in particular the threshold scheme. So it is a way to share a secret into secret shares, satisfying two conditions: correctness and privacy. So the correct condition says that any K shares can reconstruct the secrets, where K is a reconstructing threshold. And the privacy ensures that any less than K share does not reveal any information about the secrets. And in other words, if we look at any T shares of a secrets, it is indistinguishable from any T share of another secrets. So however, secret shares are vulnerable to leakage attacks. So we ask the question, what if an adversary obtains some muscle information from every secret shares? So here is a visualize of that questions. Okay. So in the local leakage model, the adversary can get muscle information for every secret. So this secret sharing scheme in leakage resilience, if the two leakage distributions are statistically close. Okay. So here we are in information theoretic setting. Adversary had unbounded computational power. So since the introductions, there has been a lot of work on this topic, and there are two main research directions. Okay. So each of them have some advantages and disadvantages. So our work belongs to the second line of research, and we study the leakage resilience of prominent schemes. So in this work, we consider two secret schemes, MASI and Shamia. Okay. These schemes are widely used in applications. So let me briefly introduce the two schemes. So the MASI schemes corresponding to a linear code, say C, and to share a secret, it sample a random code word from the linear code C, condition on the first coordinate being the secrets, and all other coordinates are the secret shares. And Shamia's special case of MASI, in which the linear codes is a real symbol code. Okay. And an important property of Shamia's scheme is that secret shares are polynomial evaluations at distinct evaluation places. And in fact, in this work, we consider the Monte Carlo constructions of these schemes. So the first scheme is MASI, corresponding to a random linear code. So what I mean is that the generator matrix of the code C is sampled uniformly at random. And for Shamia's scheme, we consider it with random evaluation places. So here is a leakage model, and this is a more general than the local leakage model I have shown you before. And the leakage function can leak global information from all the secret shares. For example, it can leak the least significant bits of the sum of all the sets. So in this model, it is leakage resilience if the two leakage distributions are indistinguishable. Okay? And again, we measure this in statistical distance. And more generally, we say that a secret sharing scheme is leakage resilience against a family of leakage if it is leakage resilience for every leakage function in that family. So with this background in mind, let me briefly summarize the prior work and our contributions. So here we have n practice and the reconstruction threshold EK.
And I want to emphasize that the smaller value of the reconstruction threshold, the better. So we want to put the liquid resilience for small reconstruction threshold. So in PDIR 18, they show that Shamir schemes in liquid resilience if the reconstruction threshold K is at least 0.85, the number of parties. And this is again arbitrary local leakage model. Okay. And the constructions is deterministic constructions, so it works for any fixed evaluation places. And 3 years later, MBSW showed that if K is at least half the number of parties, it suffices. Again, the same leakage family, but this is a Monte Carlo constructions. And they prove the massive corresponding to a random linear codes is liquid resilience. And in another work by MNPSW, they show that Shamir schemes is liquid resilience as long as the reconstruction threshold is at least 2. And it works for like almost all the reconstruction threshold. And here they consider a smaller leakage family for physical bits. So in this model, every share has lambda bits in the binary representations. And the leakage function will leak some information about those physical bits. Okay. And again, this is Monte Carlo constructions. And recently, MNPW improved the result by BDIR from 0.85 to 0.78. Okay. And in this work, we make 2 contributions, one for Massey and one for Shamir. And we consider the leakage family is an arbitrary bounded size joint leakage. And for the first result, we show that Massey is liquid resilience if the reconstruction threshold is at least 4. And from Shamir scheme, we show that it is liquid resilience if K is at least half the number of parties. And here I will note that both of the constructions are Monte Carlo constructions, so we use some randomness in the constructions. So let me state our results more formally. So in this work, we consider a secret set scheme in which every secret set is an element of a field, where the size of the field is roughly 2 by lambda, and lambda is a security parameter. And first, we show that Massey schemes corresponding to a random matrix or a random generator matrix is liquid resilience with very high probability. Okay. And the size of the leakage family is this much. Okay, so it depends only on K and the range of the leakage functions. Okay. So here's some note. We require only K at least 4, and our results bypasses the barrier due to existing Fourier approach. So in a paper by Maggi et al., they show that if we use a Fourier approach, the best one can hope for is K at least n by 2. But here we can show that for some very small constants. And this result enables secure computation of secrets. So what I mean is that these schemes have some multiplication friendly property. So this is very useful in application, in particular for secure computations. And this result is also near optimal in terms of the size of the leakage family. So in fact, there exists a leakage family of size slightly bigger than the bar we have here, so that any massive secret schemes is not liquid resilience. And we also saw similar results for Shamir. Here's the difference is that the size of the leakage family is different. Now it depends on the reconstruction threshold and also the number of parties. And it is a randomness over the evaluation places. So our results work when K is at least n by 2. And this is near optimal due to the barrier I mentioned earlier. So for the last few minutes, let me give you some high-level overview of our technical ideas. So first, we look at the Massey scheme. So our objective to show that the Massey schemes corresponding to a random generator matrix is liquid resilience with very high probability. So we use a combinatorial arguments and the second moment technique. So after a few reduction steps, to bounce the distinction about this, it suffices to put a suitable random variable. Is this one? We want to show that it is small with high probability. If we can show this, we are done. I'm not going over the details here. And to bounce this, we use the second movement techniques. And we prove that it is small with high probability by showing that, in fact, the expectations of the square of the expectation of the second movement techniques is small. And I want to note here that we prove this using the fact that the generator matrix is fully random. It is very important in our proof. And from Shamir scheme, one can think that maybe the same idea works, but in fact, it seems to fail. Why? Because here, when we consider Shamir with random evaluation places, the general matrix has much randomness. So we couldn't make the proof go through. Okay? But we observe that if we use existing Fourier approach in MNPSW21, and with the new idea of bounding the second moment techniques, we can complete the proof and showing that k greater than n by 2 works. So to conclude, the same table I have shown you before. And from this, we can see a lot of open questions here. For example, can we de-randomize all the Monte Carlo constructions? And another interesting open question is that, can we break the half barrier threshold for Shamir with fixed evaluation places? Okay. That's all I have. Thank you for the attention. I'm happy to take questions.
We have time for a couple of questions. Okay, if not, I had one quick question. So are there any impossibilities in terms of improving beyond, for instance, K4, or for instance, even for like massive secret sharing for random linear code?
Very, very good questions. Actually, we don't have any like impossibility results here. It's just some harness of computation resourcing that exists some back randomness or some back evaluation place for Shamir. But most of them are good. Yeah. Yeah.
Okay, if there are no more questions, let's thank the speaker again. So the next talk and the last talk for the day is on random index oblivious RAM. The talk would be given by Shai Halevi.
Your slides forward. Don't press the last button.
Thank you. So yeah, I'm Shai Halevi. I'll talk about random index oblivious RAM, and that's joint work with Eyal Kushilevitz. So let me just remind you what oblivious RAM is. Construct introduced quite a while ago by Goldach and Ostrovsky. You have a client that wants to access some memory but doesn't want to store it locally. So it wants to offload it to a server. It doesn't want the server to know what it's doing. So you introduce in between them sort of a compiler that runs locally at the client. And when the client wants to access a particular memory at position I, it compiles it into some query to the server answers that query, the compiler translates the answer back to the whatever was in the memory location, and the server shouldn't know what index was accessed. That's the point. In terms of efficiency consideration, the compiler should use little space and little communication, and the server space should not be much more than whatever it is to store the memory to begin with. So that's what oblivious RAM is. And in this work, we look at an oblivious RAM with a twist where the client doesn't need to access any specific index, but rather just want to sample a random index out of the memory. So now the interface is very similar, except the client asks for a sample, the compiler translates it to a query, the server answers the query, the compiler translates it now to index and whatever was in the index, and we require that the index that you sample is a random index from the memory. And again, the same thing as before, the server shouldn't learn what index was accessed, the compiler should use little space, little communication, and the server space should be small. Why look at it? Well, the obvious observation is this is a weaker primitive than full-blown ORAM because you can always implement full-blown ORAM by the client just chooses a random index and run the ORAM protocol. So maybe you can make it faster. And also it's sufficient for several applications. So an obvious one is you uncompute statistics of the memory. So you just need to sample a few things. You don't need to sample to do anything to access any specific one. You want to subsample. You're trying to figure out some graph property of whatever you have there. So you just subsample and try to compute it on the graph. In some cases, if the client is too small to even store the subsample, then you can combine it. You subsample and build a full-blown ORAM and then run the procedure. So it could be a useful property in several applications. The one that motivated this work is a lottery type application where think of people sign up with the server to participate in the lottery. The client chooses one of them at random, maybe a few of them at random to win the jackpot, and the server should know who won. Why look at that? The reason for that was it's useful for massive scale multi-party computation where you want to choose random committees. And in that application, it's in the paper, I'm not going to expand on it much, but the client, the random index client, is actually implemented via a secure MPC, so it makes it all the more urgent to try to make it as efficient as we possibly can. It's exactly the same motivation that motivated the study of random peer by Gentry et al. From last year's TCC. In the paper, we define the security notions for random index ORAM. Roughly speaking, there are two notions that we look at. There is the notion of future randomness, which is sufficient for this lottery-based applications, where the next index that you're going to look at looks random to the server, even if you have all the history of everything that happened so far. And maybe you can weaken a little bit talking about high entropy rather than fully random, but it's future looking. Then there is full randomness that says that the entire sequence look random to the server, both past and future. And just to point out what the difference is, if you only need future randomness, it's perfectly okay for you to reveal in the I plus first query whatever you were looking in the ith query, and that can help in efficiency. Other notions are batch. Maybe you want more than a single lookup at the same time. And there is another notion in the paper that's even slightly weaker than that, and I'm not going to talk about it here. We show that, yes, it does help in improving efficiency in the sense that at least the concrete construction is simpler, the specific parameters could be better. It doesn't help asymptotically because random index ORAM, for the most part, the same lower bounds that apply to ORAM will apply also to the random index version. So asymptotics, you don't expect to gain much, but it does help in terms of specific constructions and efficiency. So I'm also just going to present the high level of the hierarchical random index ORAM that we have. So let me remind you sort of on a high level how hierarchical ORAM looks like. So the server storage now consists of an order of log n levels, where level I has roughly 2 to the I slots. So the bottom level has n slots, the top one, the one above it, n over 2, etc. And when you query the server from one slot from each level. And you have the guarantee that one of these contains the right element, the one that you're actually looking for. And finding that right element is really the smarts of hierarchical ORAM. This is where sort of ingenious hashing schemes are needed in order to find it and make sure that one of them will contain the one that you're really looking for. And then the client gets all of these elements, takes out of them the one that it wants, and put it at the top. And because the top is very small, you need to continuously push things down. So every 2 to the I query, you merge all the levels from I up to from 1 up to I minus 1 into level I. And usually this is where a lot of the complexity, runtime, and etc. lies. Okay, so let's suppose we want to use this structure and we aim for future randomness. So one thing that you can see off the top, there is no right element anymore. So you don't need this ingenious hashing schemes. Every query contains an index from the previous one. So the server knows exactly what was accessed all the way in the back. In particular, the server knows exactly which item appears in what level and how many items are in each level. It just doesn't know the order of items in a level. So now the server can just return the last element from each level. The only thing that the client still needs to do is to choose one of them, and you choose them at random based on how many elements are in each level, so that to get random uniform probability over the elements overall. And then the same thing. The top level is rewritten entirely in each step, and whenever you merge it down, you need to make sure that the ordering at the level is random. You don't need any kind of placing the elements in a particular place. So again, no hashing and slightly simpler than the merging of full-blown ORAM. So this is if you wanted future randomness. If you wanted more, if you want also past things to look random, then you cannot tell the server what was fetched before. So the server in particular cannot know from which level you took the element before that. So it doesn't know how many elements are in a level, and it cannot return to you just the last one every time. But what helps you is, well, it still knows more or less how many elements are in each level. There is a fairly small window where with very high probability, the number of elements are either here or there. So there's a small window where the next element must be. So the server can just give you all of them. And you can improve a little bit if you allow caching at this client side. All right, that's pretty much all I wanted to tell you. If you want to see more, read the paper. There is a construction of tree-based ORAM. The advantage, RORAM, which the advantage of tree-based oblivious RAM is you don't need the recursive position map where you have smaller and smaller trees. So there is a log n factor improvement there. The scheme itself is extremely simple. The analysis of it is extremely not simple. And also the parameters are not great. So it would be nice to get a better analysis. Open problems, yeah, get better scheme, better analysis. One nice question is whether you can do hybrid. I want to build a structure that will allow me both to look for specific elements and to look for random elements. And I want to pay only the random elements price if I happen to just need a random element. Think of running a randomized algorithm. Sometimes you sample, sometimes you need something specific. It's easy to do if the scheme is read-only. It's hard to do if it's not. It's really interesting to do. Another nice question is whether there is a way to build full-blown ORAM from random ORAM. In the peer setting, we had a construction of a full-blown pair from a random index pair. That type of construction really doesn't work for oblivious RAM at all. We don't have any other thing, any other direction to build it. I mean, you can try to build it, one-way functions and so, but in ORAM we have even without, and I don't even know how to do that. And that's it.
Thank you. We have time for questions.
So in your definition, you require that the random index is supplied by the client at the beginning. Does it make sense to think about a variant where the random index is going to be determined at the end by the functionality?
Yeah, that's the definition. The random index is an output of the algorithm, not an input. Yes.
Oh, okay.
Thanks for the nice talk. I had so with regards to one of the last things you said, that you were not aware of a transformation from random index ORAM to ORAM and the same things that happens with peer. But so I was wondering, is there a reason to believe that the number of rounds or interaction plays a meaningful part in the difference between random index and just full-blown in the setting of ORAM, in the sense that for random index pair, the number of rounds plays an important role in the separation.
I don't think so, simply because for most ORAM scheme, it's just a single flow, right? So in the tree ORAM, you have the recursive rhyme, right? But in the hierarchical, you don't. You also need to do the. All right. Yeah, I don't know. I mean, for the tree thing, it saves something, but I didn't try to think of whether it's inherent. So I don't know. Thanks.
Any more questions? Okay, if not, let's thank Shai again. Thank you. So we'll head straight into the business meeting. Yeah, thank you.